Again, use the central limit theorem to discuss how to find a normal probability. But this one is going to be a little bit different in that we're going to have a small sample size. So let's explore this problem and see what I mean. The mean room and board expense per year at four-year colleges is $9,126. You randomly select 9 four-year colleges. What is the probability that the mean room and board is more than $10,000? Assume that the room and board expenses are normally distributed, the standard deviation of $1,500. So in this example, here's how it works. We're given a mean and a standard deviation again. We know that x follows a normal distribution with a mean of $9,126 and a standard deviation of $1,500. So the question asks, though, we have a sample size. And anytime you see a sample size, you're going to think to yourself central limit there when we see sample sizes. Two cases. The first case is if the sample size is bigger than 30. It's automatic central limit theorem. The second case is if your sample size is not bigger than 30, such as here, our sample size n is 4. So because n equals 4 is not bigger than 30, we need an additional piece of information. And that additional piece of information is they need to tell us that the distribution we're pulling from is already normally distributed. If you come down here, it says assume that room and board expenses are normally distributed. They have to tell us that to use the central limit theorem when the sample size is less than 30. So because of that, by CLT, by the central limit theorem, the mean room, the average, or x bar, is approximately normal, with the mean of that of the population, which is 9126, and a standard deviation, also known as the standard error now. And to calculate the standard error, we're going to take this value and divide it by the square root of the sample size. So it's 15,000 divided by the square root of 9. And this value, remember, 1,500 is the actual standard deviation. To find the standard error, which this value is, it should always be smaller. So 1,500 divided by the square root of 9 is just 500. So we've literally cut the standard deviation into a third of what it was by adding more numbers to the sample, made it smaller. And so now what we'll do, because we know it's following the central limit theorem, which means it's approximating a normal curve, we'll draw a normal curve. We'll label the mean of the normal curve at 9126. And I want to find the probability that the x bar is more than 10,000. So greater than 10,000. Well, 10,000 falls on the right of this value, somewhere out here. And we're going to go more than that, so we need to shade it to the right. And again, this is just a normal CDF problem. So we'll do normal CDF. The shading or the lower bound starts at 10,000. And this time it goes all the way up into positive infinity. So there we need at least 5 nines. So we have to cover the smallest or the mean value in the distribution. Then we need a mean for the distribution, which is 9126. And the standard error. We're going to put the standard error back here. This is the standard deviation. We're not going to use this term. We're going to find the standard error and put that back there now, and that's going to be 500. So we'll plug this into a calculator. So we have second vars, normal CDF. The lower bound this time is 10,000. The upper bound is 5 nines. the mean is 9, 1, 2, 6, and the standard deviation, or in our case, the standard error, because we're talking about the central limit theorem, is 500. Type that value in, and here's the value I get. I get the probability of getting a sample that's greater than 10,000 is equal to 0.04, about 4%. That's what this is saying. And again, here's how you can look at it. If the average cost for college is $9,126, then most of my colleges that I pull should be around this value. This is the true price. What are the chances that when I pull 9 random colleges, it's going to get me at a value that's this big or anything bigger than that? Well, if this is the average cost, that shouldn't happen that often. That's what this is saying. As a matter of fact, it only happens 4% of the chance, 4% of the time by chance. And so, again, we're going to use this concept of this percentage of things happening by chance later on in the units. So right now we're going to base this though off of the central limit theorem. And again, remember, the only change that you're making in normal probabilities is you're finding this standard error back here now.